Hello 5th grade, I hope that this video finds you all well. If you remember back at the beginning of the third trimester, back when we started our unit on chemistry, I remember a lot of you were asking some really good questions about, Mr. Ferris, what happens if you split an atom, and other things that pertain to the topic of nuclear chemistry. So I thought it would be appropriate here toward the end of the year to give you a lesson on nuclear chemistry. So I hope that you will enjoy it. Now, as a warning, I should let you know that nuclear chemistry can get a bit tricky and complicated at times. So this is some advanced stuff that you'll be learning here. So I'll try and introduce some big topics for you as we go through this, some key ideas to remember throughout this. I'm not going to expect you to remember every little detail of this lesson, but just some of the big ideas here. Now, before we go on, I just want to point out this little yellow symbol down in the bottom is the universal symbol for radioactive materials, and that has to do with nuclear chemistry. So if you ever see one of those symbols, don't go eating whatever it's on, because it's radioactive. When I worked in the laboratory, I used to do some stuff with radioactive materials, and we actually had that symbol on some of my projects, which was pretty cool. Alright, so first off, let's talk about this. What is nuclear chemistry? So how is it different than normal chemistry? And I should point out that it is actually quite different than all of the chemistry you've learned so far. It has its own special properties and different things going on in there. So it's going to sometimes almost throw some of the rules out the window that we've learned earlier. So you should be prepared for that. Now you notice the word nuclear in nuclear chemistry. And that means it has to do with the nucleus of the atom. So remember, back when we learned the structure of the atom, the nucleus is that clump in the middle of the atom, and it is made of protons and neutrons. And then on the outside you have these little particles, electrons, flying around the nucleus. But the middle part is the nucleus. Nuclear chemistry is going to have to do with that. So, nuclear chemistry, to give you a very brief summary of what it's about radioactivity. That's the big word I'm going to define in a moment. That is a big topic in nuclear chemistry. And it has to do with the nucleus of the atom. So then, what is radioactivity? Radioactivity is when an atom spontaneously launches out a particle or radiation from its nucleus. So I have a diagram down here in the bottom of a radioactive atom. And you can see it's just spontaneously launching out a little particle from that should be the nucleus of the atom there, and sometimes energy is released as well. So the key word here is spontaneously. It's just happening, and we'll talk about specific reasons why it might happen later. But it's just an atom just kind of deciding, I'm going to launch out a particle, and then it does, and that is radioactivity. Now, there are different types of radioactivity, and when an atom launches out a particle, that's called radioactive decay, because the atom is actually kind of decaying into a smaller atom. And there's actually 3 different types of radioactive decay. They're named after Greek letters. The first is alpha, and an alpha particle, when it's released, is basically the nucleus of a helium atom, which all we mean by that is it has 2 protons and 2 neutrons. So it's those 4 little particles all stuck together, and they're launched out of the nucleus of some atom. The second kind is beta radiation. Now, beta radiation is basically just an electron being launched out, so just that tiny little electron particle. The third kind is gamma. And gamma radiation is the kind that is not a particle, but it's actually a form of energy. It's actually electromagnetic radiation that gets launched out of the nucleus. And it is actually the most dangerous as well. So I have a chart here showing the different penetrating abilities of the different radioactive decay types. So the different kinds have different strength, so they can be stopped by different things. An alpha particle from alpha radiation is actually the weakest kind of radiation, and it can be stopped by paper. So if you want to protect yourself from an alpha radiation reaction happening in front of you, you can just hold up a piece of paper. Or just let your skin stop it, because your skin can stop it as well. Now, beta radiation actually is a little bit stronger, and it can get through the paper, but it cannot get through a sheet of aluminum, as this diagram shows. But gamma radiation can, and gamma is actually perhaps the most dangerous to people because it can, mess up it can cause mutations in your DNA and mess some things up in your cells. But it can be stopped by lead, and so that's why sometimes you'll see kind of protective lead barriers around certain types of radiation because it can't get through that. Now, I want you to remember some things about the periodic table of the elements as well right now. So first off, I want you to remember, how do you know what element an atom is? So we have an atom. How do we know what kind of element it is? The thing that makes an atom a specific type of element is going to be its atomic number, which is the number of protons that it has. So if you look at the periodic table, every element has a different number, and that is the number of protons that you can find in its nucleus. Like hydrogen has 1, helium has 2, carbon has 6, and so on. So you have the number of protons determining what kind of atom it is, what element it is. So now I want you to think for a moment about that alpha radiation. So if a nucleus is emitting an alpha particle, so it's losing 2 protons and 2 neutrons, something's going to happen to it. Remember, protons are what make an atom the kind of element that it is, but if it loses 2 protons, what's going to happen to that? And to answer that question, I want to look at one of the most famous radioactive elements, and that is uranium-238. So uranium normally has 92 protons. In fact, it always has 92 protons. The number of neutrons can sometimes change, and that's why it's called 238. Basically, the 238 is the protons plus the neutrons. You don't need to know that. It's just a different isotope of uranium is what we call that. But it's not terribly important right now. But when it emits an alpha particle, it actually loses 2 protons along with 2 neutrons. And so I'm going to think, what happens to that atom if it's losing 2 of its protons? And it's those 92 protons that make it uranium. So I have here a little snippet of the periodic table, and you can see uranium with a 92 above it, meaning all uranium atoms have 92 protons. And I'm going to think, if it loses 2, what happens to it? That atom actually then will have 90 protons, because 92 minus 2 is 90. So it ends up with 90 protons. And so it actually kind of jumps 2 spaces to the left on the periodic table and becomes a thorium atom. And for those of you wondering, yes, thorium is named after the god Thor. So that's where it gets its name. Kind of fun story behind that. So it becomes a thorium atom because now it has 90 protons instead of 92. So this is where kind of what we've known about chemistry goes flying out the window, because so far in chemical reactions, atoms never change into different kinds of atoms. They get rearranged and bond with other atoms, but they don't actually change into other kinds. But when you start looking at nuclear chemistry, you can get an atom changing into a different type of atom, and that's the big idea right here, that atoms can turn into other kinds of atoms if they go through radioactive decay. Also, I just wanted to point out, it's usually the case that radioactive materials tend to be the ones toward the bottom right of the periodic table, because those are the ones that have a lot of, or I should just say the bottom of the periodic table. They have a lot of protons and neutrons, and they can more easily kind of fall apart and decay. So it's those really big atoms that you get a lot of radioactivity in, like uranium. Okay, so here's a nice little diagram just showing you what I just told you. So on the left here we have what we call the parent nucleus, so the uranium atom that we're starting with. Notice that little 92 there? That means that it has 92 protons. And then it goes through some decay event where it just gets rid of an alpha particle. Remember, an alpha particle has 2 protons in it. So it's getting rid of 2 of those little pink protons here. And then it ends up with 90 protons, that what we call a daughter nucleus, so the atom that's left over. And that daughter nucleus is now thorium. It is no longer uranium. Okay, so then another natural question would be, why are some atoms radioactive? Why are we all not just decaying all the time through radioactive reactions? And the reason for that is that some combinations of protons, neutrons, and electrons are just unstable. They will then sometimes emit that radiation to become stable. So some different combinations of numbers of protons, neutrons, electrons, they just don't like to hang out like that. And then every once in a while, they'll just kind of alter themselves a little bit to make themselves a little more stable. I mean, we all like stability, don't we? And this leads me to the idea of a half-life, which I could spend an entire lesson on half-lives. I should probably multiple lessons on half-lives, but I want to at least introduce the concept to you right now. All radioactive materials have a half-life. So if we look at, say, uranium-238, it has a half-life of some amount of time. And that amount of time is how long it takes for half of a sample of that uranium to decay. So in a half-life, half of some amount of radioactive material will decay. It doesn't matter how much you start with, half of it will be gone after one half-life. Kind of interesting. So let's say we start with 80 atoms of some radioactive material, and we have a half-life of 1 year. So we're going to start over here on the left with 80 atoms, and then each arrow represents a half-life passing. So after 1 year, half of the 80 atoms are gone, and we're left with 40. And then, since we're starting with 40, then after another year, so after 2 half-lives, another half of that 40 is gone. So we end up with 20. And then after another year, another half-life, half of that 20 is gone, leaving us with 10. And after another half-life, another year, we have half of the 10 is gone, and we're left with 5. And we can keep going down like the 2.5, 1.25, and so on, but I'm not going to. Yeah, but it just keeps cutting itself in half, and half, and half. And it never quite reaches 0. It always just gets very close to 0, but never quite gets there, because we're only taking half of it away. We're never actually taking the last little bit away. So that's what a half-life is. You probably will hear about this later on in your scientific careers. But one thing to point out is a lot of scientists try to use half-lives to kind of measure how old rocks are, or how old some artifact is. And I would say there's certain assumptions that are being made when they do that you have to assume things, and so I don't think it's always the best science with that. But we can get more into the science of half-lives and radioisotope dating some other time. Okay, so then the big question is, how is all this useful? So radioactive stuff is cool, but is it actually useful? Like, does it serve any good in the world? And the answer is yes. First off, if you've ever watched any superhero movies, you know that the best way to become a superhero is to fall into a vat of radioactive sludge. So if you want to become a superhero, don't do that. Movies sometimes seem to misunderstand radioactivity. It doesn't actually turn people into superheroes. If anything, it causes mutations and maybe cancer and stuff like that. So don't assume that you can jump into a vat of radioactive sludge and come out as the Incredible Hulk. It does not quite work that way, as far as I'm aware. But other ways that it actually is useful is something called fission. Now, fission is just a word that means you're breaking apart an atom. So you start with an atom, and then say you launch a small neutron at it, kind of break it apart, and then you get 2 smaller atoms. As opposed to fusion, that's another word that goes along with fission. Fusion is where you have 2 small atoms that become 1 big atom. And that's what's actually happening in our sun, and that's how the sun is burning and giving off energy. We have fusion happening. So fission, fusion, fission, fusion. Now, here is a diagram of a chain reaction. I believe we can pretend these are uranium atoms. So let's say we start with 1 uranium atom, and it's near a lot of other uranium atoms, but we launch a little particle into it. We launch a neutron into it, and it's almost like like bowling. We hit that front pin with the bowling ball, and say that atom then explodes apart into 2 smaller atoms. So notice if you follow the green arrows, you get 2 smaller atoms. And coming out of it also are a few neutrons, just kind of get scattered as well. And those neutrons, they go and hit other uranium atoms. So notice here in the middle of the diagram, we have 2 more atoms that are being hit with these neutrons that are launched out. And then they explode and turn into smaller pieces. They go through fission. And then they release neutrons, which hit other uranium atoms. And we can see how this is a chain reaction, because those are going to explode and then cause other uranium atoms to explode, and it's just going to keep happening. And so this process of nuclear fission is a chain reaction that can release a ton of energy. Now, that energy can be harnessed and used to give us electricity. So if you've ever heard of nuclear energy or nuclear power plants, that is a very useful way to harness the energy from nuclear fission and get electricity for us. there's a lot of energy held inside an atom, inside the nucleus. Just like you know how when we broke apart molecules, energy is released. When you break apart an atom, even more energy is released. So you can get a ton of clean energy through nuclear fission. And that's where we get a lot of our energy from. But nuclear fission also has something of a dark side, and that is nuclear weapons. You hear of like the hydrogen bomb or the atomic bomb, these nuclear weapons that are extremely destructive. And they use the same principle that we just saw on the slide before, where we have one atom kind of being broken apart, and then it causes other atoms to break apart, and those break apart, and they're all releasing energy. And it can be a great source of electricity for us, or it can also be a source of destruction and death. It can be turned into a weapon. And now, I'm not saying that nuclear weapons are bad. They could potentially be very useful. It can help us defend good things like freedoms and religious liberty. But they also can be used in very scary ways as well. And that's why historically a lot of people have been afraid of nuclear wars. If a bunch of countries start launching these at each other, a lot of people could die, and they're very dangerous and scary. And so that's another use of radio or nuclear chemistry. But it's a scarier one. And here's a point that I want to make, and this is kind of a life lesson that applies to just about anything that you're going to learn about, especially in science. When you learn something in science, it kind of gives you almost a certain sort of power. It gives you an ability to do something. So once you know how to do chemistry, then you can manipulate chemicals and make new things, and there's all sorts of good things you can do with that. Or with nuclear chemistry, you can break apart atoms and harness that energy. But one thing that seems to be a principle anytime there's power involved in anything is the greater power there is for something, like the greater potential there is for something to be good, it could also have that same potential to be bad. So just like we can harness this energy and make electricity for a lot of people, it could also be used as a source of death and destruction and sadness. Kind of like speaking of superheroes and vats of radioactivity and stuff, Spider-Man, there's that quote, with great power comes great responsibility, and that's true. And that's why as stewards of God's creation, we need to use wisdom when we're dealing with things, especially things that are very powerful. Because while there may be a lot of really good uses for some of these things, there's also some bad uses that we need to be aware of, and we need to proceed with caution and wisdom, being able to use these things for good and make sure that they don't get into the wrong hands and make sure they're not used for evil. So remember that Satan was once the highest angel, and now he's like the lowest of the demons. The greater ability for good, the greater ability for bad. So he kind of fell from the top place to the low place. Just like when you have more power that you get through scientific study, it can be used for good or bad. So that's just a principle I want you to take with you through life. It's a good thing to be aware of. But anyways, let's go ahead and summarize this lesson. Some of the big ideas for you to take away is that some atoms are radioactive, and that means that they spontaneously emit particles or radiation. So randomly just giving off these particles or waves. Another big idea is that atoms can actually turn into atoms when this happens. So uranium turned into thorium in the example we looked at. And thirdly, nuclear fission, that splitting atoms apart into smaller atoms, can be used to make electricity and weapons. It has some very powerful uses in our world. Nuclear chemistry has lots of other uses as well. Like I used it to help make medicines, but we didn't go into that, and I'm not going to go into that right now. But here's just some big ideas to take away from nuclear chemistry. Anyways, I hope you enjoyed this lesson. Let me know if you have any questions. I know you guys had a lot of questions at the beginning of this unit, and so I hope that this helped quench your thirst for some of those answers, or maybe made you more thirsty for more answers. Both would be good. Anyways, hope you take care until next time.